Hello class, in this video we will be covering the kinetic molecular theory, the different laws to describe the behavior of gases, and molar volume. The kinetic molecular theory is a theory that explains the properties of ideal gases. There are 5 claims according to this theory. It states that gases are made up of particles that are constantly moving as shown by the arrowheads in the diagram. The volume occupied by the gas particles themselves is negligible compared to the volume that they occupy. Gas particles are in constant random straight line motions where they collide with each other and the walls of the container. The collisions between gas particles are described as elastic, which means that the total kinetic energy is conserved. And lastly, the average kinetic energy of gas particles is directly proportional to temperature. This means that as kinetic energy increases, temperature also increases, which is also illustrated in the diagram. Before we look at the different laws that describe the behavior of gases, I want to define and unpack the meaning behind 3 variables first. We will look at the pressure of the gas, the volume that it occupies, and the temperature of the system. Pressure is the measure of the force exerted by gas particles on the walls of the container during collision. This can be represented mathematically by the following formula, where pressure is equal to the force divided by the area of the walls of the container. Let's examine and compare the pressure of a system in the image on the right hand side. We can see that the amount of space or the area of the wall is smaller in the second container. Because this second container has a smaller area, you'd expect the pressure to be higher compared to the container on the left. The standard units of pressure is pascals, however there are various units that pressure can be expressed in as shown in the table along with the respective symbols. Because pressure can be expressed in different units, it's going to be an important skill for us to learn how to convert between the different units of pressure when we perform calculations in future videos. Fortunately, the VCAR data booklet contains a table which outlines how to convert between kilopascals, millimeters per mercury, and atmospheric pressure. However, to start off, I think using the following flowchart will be easier to use. As you can see, atmospheric pressure lies in the center of the flowchart. As a result, it might be necessary for you to convert the original pressure unit into atmospheric pressure first in order to express it to the desired pressure unit. Let's have a look at a few examples. In part A, we need to convert bars to kilopascals. To do this, I will need to convert bars to atmospheric pressure first by dividing by 1.013, and from here, I need to multiply by 101.325, giving me an answer of 33.7 kilopascals. In part B, we need to convert 253 millimeters of mercury into atmospheric pressure. This can be done directly by dividing 253 by 760, giving us an answer of 0.333 atmospheric pressure. In part C, we need to convert atmospheric pressure to kilopascals by multiplying by 101.325, giving us an answer of 33.7 kilopascals. And for part D, to convert from millimeters of mercury into bars, we first must convert it into atmospheric pressure by dividing by 760, and then using this answer, we can convert it into bars by multiplying by 1.013, giving us an answer of 0.337 bars. The next variable that I would like to talk about is volume. Because gases take up the space of a container, the volume of a gas equals to the volume of the container. The volume of gas can be described using various units. You're probably used to seeing milliliters and liters as units for volume, but other units for volume also includes cubic centimeters and cubic meters. As you can see in the diagram, 1 cubic centimeter is equal to 1 milliliter, hence 1000 cubic centimeters is equal to 1 liter. Fortunately, VCAR has generously given us the conversion factor to help us convert between different units for volume. Let's have a go at converting between volume units in a few examples. Because we know there's a 1-to-1 ratio between milliliters and cubic centimeters, 255 milliliters is equal to 255 cubic centimeters. For part B, we can convert milliliters to liters by dividing by 1000, giving us an answer of 0.255 liters. And for part C, we need to convert volume in cubic meters. There's many ways you can go about this, but since I know that 1 liter is equal to 1 times 10 to the negative 3 cubic meters, I can multiply 0.255 with this value over here, and in doing so, this will give me a value of 2.55 times 10 to the power of negative 4 cubic meters. As I've stated earlier in the video, the temperature gives us a measure of the average kinetic energy possessed by gas particles. Temperature can either be measured using the degrees Celsius or Kelvin scale, hence it's important for us to be able to convert between these units. The lowest temperature in degrees Celsius where particles have zero kinetic energy is negative 273 degrees Celsius, which is often referred to as absolute zero and is the benchmark of the Kelvin scale. As you can see, negative 273 degrees Celsius is equivalent to 0 Kelvin. Hence, to convert from degrees to Kelvin, we simply need to add by 273, and we do the opposite to convert back as shown by the two equations. I would like to add that there is no degree circular symbol when we're expressing temperature in Kelvin. Now that we've covered pressure, volume, and temperature, let's learn about the different gas laws that describe the behavior of ideal gases. Boyles Law states that when you've got a fixed amount of gas at constant temperature, volume is inversely proportional to pressure. This means that when the volume of gas is low, the pressure exerted on the walls by the gas is high, and vice versa, as you can see in the animation. If you also look at the animation carefully, we could also see that the ratio of pressure and volume is constant. As a result, we can write an equation P1 times V1 is equal to P2 times V2, and this formula can be used to calculate the starting or final pressure or volume of gas, given that the amount of gas and temperature doesn't change in the system. Charles' law states that volume is directly proportional to the absolute temperature for a fixed amount of gas at constant pressure. This makes sense because if you increase the kinetic energy of the gas particles, what you are doing is you're increasing the number of collisions. However, if you want the pressure or the force to remain the same, volume needs to increase, and this is also shown in the animation. Because the ratio between volume and temperature is constant with a fixed amount of gas and pressure, we could use Charles' law to find the volume or temperature of gas under different conditions with the equation down below. The next law that I want to talk about is a pressure law, which states that pressure is directly proportional to the absolute temperature for a fixed amount of gas at constant volume. At low temperatures, the kinetic energy is low, hence the collisions and the force applied to the walls will also be low. However, if we increase the temperature by heating it up, the gas particles will have more kinetic energy, moving faster and thus more force on the container walls. The relationship between the amount of substance and volume is discussed in Avogadro's law. It states that the volume of the gas is directly proportional to the number of moles of gas when temperature and pressure are held constant. This makes sense because if you got more particles present, the amount of space the particles will take will also increase if we want the pressure to remain constant. Now that we've covered the different gas laws, I would now like you to apply your understanding of the gas laws to answer the following question. Pause the video now and play again when you're ready to check for your solution. In this question, you've got two bottles with the same volume and temperature. Each bottle contains different elements with the same mass, and we want to compare the relative number of atoms and pressure. To compare the number of atoms, we first need to find the number of moles of argon and neon. From these calculations, we can deduce that the number of moles of neon is double of that to argon, hence we can eliminate options A and B. Because the number of particles are doubled in bottle 2, while the volume and temperature is constant, you'd expect more collisions in the same volume, hence more pressure. As a result, the correct answer is going to be D. The next thing that I would like to talk about in this video is molar volume. The molar volume is defined as the volume occupied by 1 mole of gas at a particular pressure and temperature. If you look in the following diagram, we've got 1 mole of neon, nitrogen, and ozone. Notice how each of these three gases have the same volume of 22.7 liters under the same conditions regardless of the type of gas present. We can express the relationship between the number of moles, volume, and molar volume with the following formula. There are two main experimental conditions that scientists normally perform their test in. When experimental conditions are at 0 degrees Celsius and 100 kilopascals, it's found that the molar volume of any gas at STP is 22.7 liters per mole. In other words, 1 mole of gas under these conditions will have a volume of 22.7 liters. When the temperature is 25 degrees and the pressure is 100 kilopascals, we refer to these conditions as standard laboratory conditions. Under these conditions, the molar volume is equal to 24.8 liters. Fortunately, the data booklet specifies the molar volume under SLC, so you will only need to memorize the molar volume under STP. Let's look at some simple calculations that relate to molar volume. In the first example, it's asking us to calculate the number of moles of chlorine gas present in 48 liters under standard laboratory conditions. We can calculate this using the formula N is equal to V over Vm. Since we know that molar volume is equal to 24.8 liters under SLC, plugging in these values will give us an answer of 1.94 moles of chlorine gas. In this second example, it's asking us to calculate the mass of hydrogen gas when the volume is 1,556.5 milliliters. In order for us to find the mass of hydrogen gas, we need to find the number of moles first, which can be found by using this formula over here. However, please bear in mind that we need to convert this volume into liters first. Substituting these values into the formula should give you an answer of 0.0627 moles of hydrogen gas. To find the mass, this can be calculated by multiplying the number of moles with its molar mass, giving us an answer equal to 0.13 grams. In the last section of this video, we're going to look at calculations using the combined gas law. The combined gas law was derived by combining all the different gas laws and shows the relationships between pressure, volume, and absolute temperature of a system with a fixed amount of gas as shown in the equation down below. This equation is useful for us to solve for a variable when you have a fixed amount of gas that undergoes a change in conditions. There's a few things that I would like to address when you're using the combined gas law. Firstly, we could use any units for pressure and volume in the formula as long as the units are consistent with one another. However, temperature must be converted and expressed using the Kelvin scale. In this example, it reads a sample of air at 10 degrees Celsius and 1.1 atmospheric pressure has a volume of 2.2 liters. If the pressure changed to 1 atmospheric pressure and the temperature has increased to 15 degrees Celsius, what volume will it occupy? In this question, we're trying to find the final volume, which is represented by V2 in the equation. Before we can plug in the values into the formula, please remember to convert degrees Celsius to Kelvin, which I've done in advance as you can see over here. From here, we can plug in the values into the formula and rearrange to solve for V2. This can be done by multiplying both sides of the equation by 288 and then dividing by 1.0, and if you put this into the calculator, you should get an answer of 2.5 liters. I would now like you to solve a similar problem. Pause the video now and resume again when you're ready to confirm your solutions. In this question, we want to find out what is the final pressure, or P2. If you plug in the values into the formula correctly and transpose it, you should have obtained an answer equal to 1.31 atmospheric pressure. By now, you should be able to meet the success criteria in this video. If you found this video helpful, please like the video. Thank you for watching, and I hope to see you guys again in the next one. Bye.